So this is an instructional video on how to do a DEPT experiment for an NMR spectrometer running varying VNMRJ. So DEPT experiment is distortionless enhancement by polarization transfer, and the goal of it is essentially to get more information than you would in a standard C13 experiment. Specifically, you're looking for multiplicity, meaning are the different carbons CHs, CH2s, CH3s, etc. So first, you're going to want to do your standard C13 experiment. I'll join experiment 22 because that's where I have one saved. Display the spectrum, and here we see a standard carbon experiment for an ethyl crotonate. So the ethyl crotonate has all types of carbons. It has a quaternary, it has CH, CH2s, and CH3s, and we want to be able to determine what is what with multiplicity. So we're going to use a standard DEPT experiment. Join new experiment 3 and load a DEPT experiment. I'm going to do that by typing DEPT with a capital D, and here we have a pulse sequence for a standard DEPT experiment. So this pulse sequence, I want to point out a few things. Here we have D1. This D1, the relaxation delay, is dictated by the relaxation time of the proton spectra. So if you have a compound that you're looking at that has a long proton relaxation delay, you're going to want to change D1. The other important thing is this. Here it's titled J tau, and this is the transfer delay. So 3.6 is 3.6 milliseconds. If you go under pulse sequence, that's 3.57. That's the transfer delay that comes from 1 over 2J being calculated from. So this transfer delay is being calculated from the average proton-carbon coupling constant. The other variable that you want to pay attention to is this one, the multiplicity. So the multiplicity is what is going to determine which peaks you see in the DEPT experiment. So multiplicity could be either 0.5, could be 1 or 1.5, and that's going to change this proton pulse. If it's 0.5, we get a 45-degree pulse, and we're going to observe all types of peaks with the exception of quaternary peaks. So we'll see CHs, CH2s, and CH3s. If multiplicity is 1, we're going to get a 90 pulse, and we're going to observe only the CHs. All the other peaks will be gone. And if multiplicity is 1.5, we're going to observe a 135-degree pulse, and CHs and CH3s will be phased together in phase, and CH2s will be out of phase, anti-phase. So we'll get CHs and CH3s up and CH2s down. So with that information, we can determine which of your carbon peaks correspond to which multiplicity. So in order to do this experiment, we'll just go through these. So under defaults, you can adjust your spectral width. JXP22 and DS to show our original carbon spectra, and that doesn't go any past 170, so maybe 190 downfield should be fine. So we will change that to 190 downfield. Relaxation delay, we can change that if we feel necessary, depending on the T1 time of our proton channel, or of our protons. Number of scans, definitely want to increase. Here 256 is good. Now in the CH multiplicity, this is going to change your multiplicity value here. Now we've already done a standard C13 experiment, so instead of doing full editing where the time is going to be 35 minutes, we can choose any of these, and in this case I'm going to choose CH and CH3s up and CH2s down. When we showed time, that's much shorter. That's only an 9 minute experiment. As you continue down, acquisition, again you can change either acquisition delay or relaxation delay depending on if you need to. Maybe Maybe you need to if your FID hasn't decayed well enough. Your pulse sequence, this is where you can change the transfer delay depending on what you think your average one bond proton carbon coupling is, or if you're not sure, just keep it as 140. Under channels, this is where you have carbon as your observed channel and you're decoupling onto the proton channel. Don't need to change the carbon channel. The proton channel, you can just look through and change the decoupling if you want. Default is no, no, yes, meaning you're going to be decoupling here at the end and you're decoupling with a W for broadband waveform. And you want the broadband so you can decouple the entire proton spectra. Last thing, under flags, you want to change this save FID at each block, scans per block, to say 16. That way, if you Fourier transform every block size, you'll be able to get the experiment done faster if you have a high enough signal-to-noise ratio. You can ignore future actions, and now we can just type go. It's not hooked up to the spectrometer, so this one isn't going to work, but I have this spectra here on 33 with this multiplicity, and we can type WFT, APH to autophase if we want, and here we have 5 peaks. One peak is missing, which was around here, so that tells us that this peak must be quaternary carbon. We have these phased up, these phased up, this phased down, so this one must be our CH2. Now what we want to do is create another experiment, or join another experiment 4, and then move the parameters from 3 to 4. So we're making an identical experiment in 4. The only thing we're going to change now is, under defaults, CHs only. So that'll change the multiplicity to a 90-degree pulse at the end. Multiplicity equals 1. The only thing you need to do is change that, and again type go. It'll just add this to the queue if experiment 3 is still running. So now that at the end you'll have experiment 3 and experiment 4 done. Here I have the spectra for experiment 4, which has multiplicity equal to 1. Display the spectrum, and here we have, again, the quaternary carbon peak is missing. We have these two, which mean CH2s, because we only expect CH2s to be visible, and the other peaks were greatly reduced, if not completely eliminated, which is also what we would have expected. So combining all this information of your original carbon spectra, this one, with 6 peaks, this one is going to be your quaternary because it is missing in your other spectra. These are your CHs because they showed up in your 90 pulse at the end with multiplicity equals 1. This one is your CH2, and these are your CH3s because they did not show up in your 90 pulse, but they did show up in your 135 pulse.